Now, there's two reasons that we deal with this. I know many students already know derivatives, how to do the mechanical process, but we need to understand what a derivative is for applications. And there are some functions that you cannot go by shortcut rules, so we need to understand this tape. So let's go through the first process. We're given f of x is equal to x squared plus 3x minus 1. And we want to find this derivative by the definition. Well, the definition of a derivative says, in the middle of your paper there, that it's the limit of f of x plus h minus f of x all over h as h approaches 0. Now I'm going to discuss later in this tape really what that's saying, but right now we're going to say that's the definition of a derivative by what is called the difference quotient. So that means what we would need to do is come do this. Well, in function notation we learn to do that. So let's just go back up and put these two things together. There we have two different tapes, one on function notation. So first let's find what f of x plus h is. All right, so step one is to find f of x plus h. That says I'm going to replace x plus h wherever this object is. Whatever this is, I replace it with x plus h. So over here I will put x plus h squared, and over here I'll put x plus h. So let's expand that out. So expanding that, we get x squared plus 2hx plus h squared plus 3x plus 3h minus 1. So step one is to replace the x with x plus h, expand that out, then come along and rewrite what f of x is, which is x squared plus 3x minus 1. And step two then is to come over here and subtract them. So if I subtract this from this, that's what I get on the left side. It's I subtract on the right side, that drops out, that drops out, that drops out, and we have left 2hx plus h squared plus 3h. That's step two. Step three then is to come along and divide this side by h. Divide this side by h. Well, what we'll do is factor an h out of that, and we're left 2x plus h plus 3 all divided by h. And what happens now? These divide out. And so we have left at the difference quotient process here is 2x plus h plus 3. Now that's our algebra. Then the next step of the definition is to say, all right, what we want to do now is to take the limit of this as h approaches 0. Well, what happens when h is 0? We get this then to be 2x plus 3. So we then say that the derivative of the function is 2x plus 3. Now, let's step back and look at all this and listen to the steps and just learn this mechanical process. Step one is to replace x with x plus h. Go expand all that. Subtract the original function from it. Okay? Divide by h. And when you divide by h, you're trying to get rid of this h in the denominator. I'll explain in a minute why. And then that means we'll factor out an h. It will divide out. And then we take the limit of what's left as h approaches 0. In other words, put 0 wherever the h is. Well, you see, why we need to factor this out is because if we put a 0 where the h is, before we divide, we have a 0 in the denominator. We do not want that. So that's the purpose of doing all this and factoring the h out to get rid of that denominator. Then plug in 0 where h is, and that is the derivative of the function by the definition process, what's called difference quotient, in case you hear that terminology. All right, let's look at the next example. And again, this is just a bunch of algebra right now. Okay. All right, so we have the function f of x is 7x cubed. So step 1 is f of x plus h is 7 times, replace h cubed, minus 5 times x plus h squared, minus 10. All right, now, expanding this, I'm going to kind of move over here and take 2 steps. It would be 7 times, all right? First one cubed, plus 3 times the first one squared, last one, plus 3 times the first one, last one squared, plus the last one cubed, minus, excuse me, let me put parentheses here, minus 5 times this squared, plus 2hx plus h squared, minus 10. Now let's get all that simplified. So we'll have 7x cubed plus 21x squared h plus 21xh squared plus 7h cubed minus 5x squared minus 10hx minus 5h squared minus 10. Well, that's all f of x plus h. Now what do? We now subtract from it the original function, which was 7x cubed minus 5x squared minus 10. And we subtract that, and we get left 21x squared h plus 21xh squared plus 7h cubed minus 10hx minus 5h squared. Okay. So we have now step 1, step 2. Step 2, we've got it subtracted. Step 3 is to divide by h. Okay. So we're going to divide this by h. Well, what are we going to do? Factor out an h. So we're going to take an h out of everything here. That's going to leave us 21x squared plus 21xh plus 7h squared minus 10x minus 5h. And look what happens. We're going to now divide that h out. And now we're going to take the limit of it as h approaches 0. In other words, we're going to come in here and put a 0 where the h is. So that drops out, that drops out, that drops out. So our final answer to the derivative is 21x squared minus 10x. That is the derivative of the original function, okay, done by definition, difference quotient. All right. Turn the page now. Let's look at the next example. Now, what I'm showing these 2 examples for are for you to be able to do some of your homework that's usually assigned for the algebra concept. All right, so what do we do? Step 1. Step 1 is f of x. So I come over here and replace this with x plus h. Okay, then I come down here and put this, and I subtract it. So then that's 1 over x plus h squared minus 1 over x squared. Okay, so we have step 1, subtract them, step 2. Well, we have fractions here. So before we do step 3 and divide by h, let's get the fractions combined by common denominator. So common denominator would give us x squared minus x plus h squared all over x squared x plus h squared. Okay, well, let's see. This squared is, let's just rewrite that, is x squared plus 2hx plus h squared. And then when we remove the parentheses, the x squares drop out, and so we have on top 2hx plus minus times this is a minus times this is a minus, h squared, all divided by x squared, x plus h squared. All right, good. Now we got it all simplified. Now what do? Remember, we factor out an h and divide it out. So we'll factor an h out of this and then divide that by h. And what happens? Those drop out. So now look what happens. We now have, here's our simplification of the difference quotient. We now say the limit of this is h approaches 0. Well, when h approaches 0, that drops out. And look what happens here. We get an x squared and an x to the fourth. So we have 2x over x to the fourth, which simplifies to minus 2 over x cubed. Okay, so as you do your homework, you have some algebra process in here, but it's still step 1, replace x with x plus h. Step 2, subtract them. Step 3, do the algebra here, factor, divide out the h's. And step 4, let h equal 0, and that is your answer. All right, let's look at the next example. And again, this one's for learning some algebra concepts that you need to know. So we have f of x is the absolute value of x. So we come along here and we say, okay, what is f of x plus h? Well, we replace this with x plus h. Then we come along with writing the original function down and we subtract them. So what we have is the absolute value minus the absolute value. Okay, so there it is. We want to divide by h. Well, when we try to divide by h here, there's no factoring process. It won't divide out. This will not work with dividing by h here. We cannot get rid of this, so we can't go to the next step and take the limit and let h approach 0. Won't work. So what we must do is come in here and multiply the top and bottom by the absolute value of x plus h plus the absolute value of x plus h plus absolute value of x. This is called a conjugate process, okay? So we're going to multiply this by its conjugate. That way when we do the FOIL method, we have no middle term. All right, so first times the first is x plus h squared minus x absolute value squared over h times, and don't multiply this in, just leave it this way. All right, so we have that. Well, here is where we need to learn something about absolute value if you don't already know it. So let's come over here to the side for a minute and just discuss this. All right, the absolute value of x says that it's equal to x if x is positive, and it's equal to a minus x if x is negative. That's one definition. Another definition says that the absolute value of x is equal to the square root of x squared. That's not a bad idea. Look, if x is 5, what is 5 squared? 25. What is the square root of 25? It's a positive 5. Okay? Because whatever the sign is in front of this. When you do a square, when you have the square root sign written down, it's whatever the sign is in front. Well, if x is a minus 5 and you square it, you get 25. And what's the square root of 20? It's also 5. So, that means then, if I have the absolute value of x is the square root of x squared, and I square this, then it must mean that it's that squared. In other words, it's whatever is inside squared. So the absolute value squared is whatever the inside is squared. So let's go back to our problem now. So this means then that the absolute value of x plus h squared now becomes parenthesis squared parenthesis squared. And what do we get there? Well, we get x squared plus 2hx plus h squared minus x squared all over h times x plus h plus, and look what this drops out. And here we factor again. So we're going to factor and divide the h out. And so we have left 2x plus h over absolute value of x plus h plus absolute value of x. Now we do what? We take the limit of this as h approaches 0. Well, if the h is 0, what do we get? We get 2 of these. So on the bottom, what we get then is 2 absolute value of x's. 2's drop out, and therefore the derivative of the absolute value of x is x over the absolute value of x. Now I'm going to discuss this later in this tape about slope and say, hey, we could have gotten that answer just to start with by a reasoning process. Okay, now let's look at another concept of the definition of derivative. All right, another concept of the definition of derivative is this, written in the notes there in capital letters. It is the slope of the line that is tangent to the curve at any particular point. In other words, the derivative of this function. When I get that answer, 2x minus 4 or whatever it is, then that happens to be, if I go plug an x value in there at this point, I will get a slope of whatever this tangent line is to that curve. Now let's understand why, how all this works together. All right? So we're going to go from this point P to the point Q. And we're going to increase by h. We're going to go from this point P and come over here a distance of h to this point Q. Well, this point is x for the x value and f of x for the y value. That's the same thing as y. Okay? And so if I'm going to increase this, then now my x over here at Q is x plus h, and my y is f of x plus h. So what is the slope of this line that connects those 2 points? The slope, then, would be the y minus the y. Well, that's f of x plus h minus f of x. And then it would be x plus h minus x. The slope of this line would be the y minus the y over the x minus the x. Hey, look at there. These x's drop out, and look what we have. We have a difference quotient concept. So that's the slope of this wiggly line, slope of the wiggly line. All right, now let's bring point Q back closer. Let's let x not be so large. And there's that line. And let's bring h back here closer, and there's that line. And what happens when h is almost 0, when point Q is almost next to it, is the tangent line. So as h is getting smaller and smaller and smaller and closer and closer and closer to 0, in other words, when we take the limit of this as h approaches 0, what we're getting then is this line out here that just touches once. When these 2 points become so close together that they're a single dot almost, then that becomes, that if you connect those 2 dots and extend it, it becomes the line that's tangent to this curve at this point. That's what that gives us then. So that limit of f of x plus h minus f of x divided by h as h approaches 0 gives us slope of the tangent line. Remember, now this was slope. Before I wrote the word limit in here, this was slope. It doesn't give us the tangent line. It only gives us the slope of the tangent line at the point X. Okay, well that becomes extremely important to work some problems where we can't use a shortcut method. Well, let's look at that for a couple of examples that you usually have in all textbooks and homework and test problems. So the next example I want to work is to show you how this works to do homework problems. All right, this problem says I have y is equal to x squared plus 3x minus 1. Remember, that's one of the first examples we did. And we want to find the slope of the tangent line over here when x is 1 and y is 3. We want to find the slope of that. Not the equation of that yet, just the slope of it. Well, what we do is go find the derivative of this. And we go do that. Remember, we've already done it. The derivative of this was 2x plus 3. So that's the derivative. All right, at 1, 3, what does this mean? What does the 1 mean? That means x is 1, y is 3. So x is 1. So I go put a 1 right there. 2 times 1 is 2, plus 3 is 5. So the slope of this line right here, slope of this tangent line, is over 1 up 5, slope of 5. So what we can do then is take the x value of a point and plug it in the derivative and find the slope of the tangent line to the curve at that point. Now this has a bunch of tangent lines. So all we're finding is the slope of the one at the point 1, 3. All right, now let's go to the next example, the bottom of the page of the notes, and look at a typical homework problem. The problem says this: find the equation of the line tangent to the curve and the line normal to the tangent line. That's not the way the words say that, but that's what it says. Find the equation of the line tangent to this curve at the point 5 minus 3, and we want the line that's normal to the tangent line. Well, or to the curve. Normal means perpendicular. In other words, looking at this right here, what we have is, say, a graph like this. There's the tangent line, and the normal line then becomes perpendicular to the tangent line at the same point. All right, well, I'm not going to work through all this. We've done this, but here it is. It's all set up. What we do is go find the derivative of it. We go find the derivative, difference quotient, so we come down here, and we find the derivative is that. Okay, so looking at this now, that's the derivative, and we want to say at, okay, 5 minus 3. So if I plug a 5 in here where the x is, I get a minus 6. So the slope of the tangent line, is a minus 6. Now let's go do the work for what the question asks. All right, so let's come over here and look. Here is the formula or equation for the equation of a line. If we're given a point that it goes through, here's 5 and a minus 3, and a slope, which is the minus 6. So we plug in. Okay, y is equal to a minus 3, and we plug in the slope here, and we have x minus 5. Okay, and then we go do the algebra. Well, I'll go ahead and go through this algebra. Minus 6 times x, minus times a minus is plus 30. Now, learn to write the equations this way nowadays. This is a minus 6x plus 27. Learn to write equations, y equals, and then x's and numbers. And I think the reason for doing it today was because of calculators, okay? You go graph it and go work with it. That's the way you're going to see it. Textbooks now, they may make you move this over and put what's called standard form. That's not what's important to learn on the tape. All right, so that then is the equation of the line that's tangent to the curve at the point 5 minus 3. Hey, look, if you remember your analytical geometry or algebra, equation of the line, y equals what? Slope plus y-intercept. So sure enough, it checks. We get a minus 6 for a slope. Okay, now that's the equation of the tangent line. Now what we want to do is find the equation of the normal line. Well, again, reviewing your math that you previously had, if a line is perpendicular, then it's the negative reciprocal. The negative reciprocal. So the negative reciprocal of that is positive 1/6. Now, I would like to show you what I think is the best way to work this one. When you have a fractional a slope right here, learn to do this. Just take the denominator and multiply it that side. And the numerator times this side. Okay, and then go work it. Okay. So let's go ahead and this will be 6y is equal to x minus 23. Dividing by 6, I get 1/6 x minus 23, 6. Again, look, what's the slope of the line? 1/6. It checks out. Okay. Now, let me just, this is not on the tape, but on the notes, but let me just show you something. The reason I like this method is for this reason. Is what happens if the slope is 0? Okay? What happens if the slope is 0? Slope is 0 over 1 or 0 over 5 or 0 over 10. Well, what do we get here? 1 times that is y plus 3. 0 times this is 0. You move it across, and sure enough, it ends up being minus 3. Well, what happens if the slope is vertical? If the slope is vertical, that's 1 over 0. 0 times that's 0. 1 times this is 5, and so x equals 5. So using this concept, it works for all cases in a very easy way of working it. Okay. Now that shows you the definition of what a derivative is by the concept of slope of the tangent line. It shows you how to work a problem about finding the line tangent line normal to the curve at a point. Now what I want to do is to show you some thinking processes of what the definition says. All right, now let's look at the examples where we have to use a thinking process and a reasoning process about the definition of the derivative of a function. We want to find the derivative of the function sigma x. Okay? Well, what is the definition of that? Well, the definition of that says this. If x is positive, then the answer to all of this is plus 1. If x is equal to 0, the answer to all this is 0. And if x is a negative, negative 5, the answer is minus 1. If x is minus 10, the answer to all that is minus 1. Okay? Now these have usage in other parts of mathematics, so it's not just a total waste of time. So what is the derivative of that? Well, let me go ahead and graph this thing. It says when x is 0, y is 0. When x is a little more than 0, then it's 1 coming out here. When x is negative over minus 1, minus 2, minus 3, then it's going to minus 1 all the time. What is the slope here? 0. What's 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 the slope here? 0. Therefore, the derivative of that function is 0. Because its slope is 0. Not because of algebra, not because of anything else, but because I know what the slope of that is every place, and therefore I know the answer to this to be the derivative is 0. Let me talk about something here that I wanted to talk about a while ago. What happens about the absolute value of x? Okay? What is the derivative of the absolute value of x? Well, let's graph this and see if we can come up with it by a reasoning process. If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2. If x is minus 1, y is 1. So we get that. So what is the slope over here? X is 1, 1, 2, 2. Slope is 1. The slope of that is 1. So the derivative, that's 1. But wait a minute. Over here, it's a minus 1. Well, look what happens. If I write x over the absolute value of x, if x is 5, I get 5 over 5. That's 1. If x is 10, I get 10 over 10 is 1. If x is 1, it's 1 over 1 is 1. So over here, when x is positive, I get 1. Well, Well, when x is a minus 2 over a plus 2 is a minus 1. A minus 5 over a plus 5 is a minus 1. A minus 7 over a plus 7 is a minus 1. So that describes plus 1 when x is positive and minus 1 when x is negative. So this describes the derivative of that, okay, by knowing the graph of the slope. And we don't have to do all that algebra. All right, now let me go back to this just for a moment about your TI-92. I don't think it's in other calculators, but in the 92, what that's done as is the sine of x. Okay, I mean that's just the way that comes out. And so if you go work with that, you go do SIGN parenthesis 5, you'll get a 1. Minus 5, you'll get a minus 1. The thing I don't think works with 0. It's not defined in there. So what happens when you get 0? It doesn't give you 0. So calculators can't do everything. Well, hey, you know what it does? If you go find in the 92 the derivative of the absolute value of x, it gives you this. It gives you that for the answer. Instead of what I say is x over the absolute value of x, it will give that, which is saying the same thing. When x is positive, this is a 1. When x is negative, it's a minus 1. So using a 92 on stuff like that, that's what you find out. All right, let's look at the next example. Finding the derivative of the, okay, what I call bracket x. And what we need to learn now is this type of thing. In some textbooks you'll see this, some you'll see just the marks on the bottom, and then they may have just the marks on top. Okay? And I'll discuss that briefly here in a minute. But what I want you to know is this. Bracket x is, if I put a 5 in there, then the answer is 5. If I put 5.1, the answer is 5. If I put 5.2, the answer is 5. 5.4, the answer is 5. It goes back to the greatest integer on the left. Now this is what this stuff does. That's what this is saying. I want to go back to the greatest integer on the left. This says I want to bump it up to the integer on the right. All right? So I'll just stay with bracket x. All right, bracket of a minus 0.13 is a minus 1, not 0, goes that way. Okay, so minus 1/2 goes to a minus 1. A minus 1 1/2 goes to a minus 2. Okay, goes to the greatest integer going back to the left. Well, look, here's what this graph is. 0.1 is 0. 1/2 is 0. So 1 1/2 is 1. 1 3/4 is 1. 2.1 is 2. 2.5 is 2. 2.9 is 2. So what we get then is this bracket, and this has a lot of uses. For instance, Postal Service. Everything between 0 and 1 ounce is 32 cents. Everything between 1 ounce, 2 ounces is 64 cents, and so on and so forth. So you can use this for writing different kinds of equations. Now what I'd like for you to remember is what this is a worm crawling over a razor blade, okay? So if this worm crawled over this razor blade, that's what would happen. All right, well, derivative. What is the derivative? Well, what's the slope here? 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 Therefore, the derivative is 0 because the slope is 0. So the derivative of this function at values not exactly 1, not exactly 2. See, there's a gap there, so it doesn't have a derivative exactly 1. But numbers between 1 and 2, the derivative is 0. Between 2 and 3, the derivative is 0. All right, so there's two functions that you have to come up with the derivative by knowing what the slope of the curve is. Okay, not by any algebra or mathematics or shortcut rule. All right, now let's look at on your notes where it says graphs. So let's look at problem 27. Now what it's asking is we want to take this problem and go look above there and see which one of those graphs best represents the derivative of this, Now remember now, this is x and this is y. The derivative then, we're going to come down here and plot x and y prime. What is the derivative equal to? The value of the slope. For instance, what is the slope of the tangent line here? It's 0. What is the slope of the tangent line here? It's 1. What is the slope of the tangent line here? It's 2. What is the slope of the tangent line over here? It's -1. What is the slope? It's a -2. Now we're going to go plot those values. On this graph, we're going to plot with respect to the value of the slope. So therefore, the slope here is 0. The slope here is 1. The slope here is 2. The slope over here is a -1. The slope is a -2. And so we get this line. All right, so that's part B. Now listen to me. We're graphing the value of the slopes in this direction. The y prime is our y-axis. And so we're saying, okay, the graph of the slope, the tangents here, happens to be this. And if you do that, if you'll take your calculator, and you can do this on the 92 and on the 85 also, if you will graph the function and then graph its derivative, okay, on the 85 you have to go find the values to do that. You will get then, this graph will be the graph of the slopes. The graph of the slopes. So what we're doing, and listen to this for importance of the example 31, 32, is what we're graphing down here is the value of the tangent line, the value of the tangent line, the value of the tangent line. And so we get that particular graph. Now, I want to inject in something here. The equation up here is y is equal to x squared. And if you go take the derivative, this power will come down by 1. Okay, it'll happen to be a 2 there, but anyway, it'll come down by power 1. So this is x. Y prime is equal to x. That's linear. Okay, it's linear, so it's a straight line. So if this is a parabola, the derivative would be a straight line. Okay? So now let's look at number 28 and see what happens on it. Okay. Now 28 is a cubic equation. Just to jump ahead a minute. 28 is a cubic equation. This is y is equal to x cubed. So the derivative is going to be x squared, something x squared, which means this better be a parabola. Well, let's see if it is. What is the slope here? Slope here is, well, over here, slope is +1, +2, +3, and over here it's a +1, +2, +3. Well, let's see. Graphically, what does that say? Here it's, well, we don't know for sure exactly. Over here it's 1. Over here it's 2. Over here it's 3. Over here it's 1. Over here it's 2. And so what we get then is something like that. And what happens? This is 1 and then 1/2 and then 0 and then +1/2, so it's 1/2 and then 0 and 1/2 and so on. So therefore this is the derivative, y prime, okay, for this curve up here. All right, so that's why 28 matches. Now, let's see about 29. All right. Okay, looking at this one, a lot of curve to it, a lot of different tangent lines, so let's look now. All right, let's start right here. The slope is 0, so that's 0. Slope is a -1, so that's a -1. Slope is a -2, -2. Slope is a -3, -3. Slope is a -5. Then it slopes back to a -4, -3, -2. So it comes back here. And here the slope is 0. So the slope is 0. All right, then the slope is a +1, plus 2, plus 3. Gets up here, then it starts back to 3, 2, 1. So it comes back. All right, over here the slope is a minus, slope is 0. Slope here is a positive 1, excuse me, slope is a positive 1, positive 2, positive 3, positive 5, and then positive 4, 3, 2. So it goes to positive 5, and then 4, 3, 2, and then back to 0. So here's 0. All right, over here, its slope is a minus 1, minus 2, minus 5, and then back to minus 3. Comes back to that way. So therefore, number 29 is the D. Okay? All right. Well, obviously, then that makes number 30 C, but let's see why. So let's look at 30 and see what we get here. Okay? Looking at 30. All right, let's graph it. The derivative. All right, the derivative here is 0. The derivative here is a minus 1/2, a minus 1, a minus 2, a minus 1, a minus 1/2, 0. Plus 1, plus 2, plus 3, plus 4, and just keeps on going. So this one comes over like that. Now over here, the slope is a the slope here is a positive 1, positive 2, then it comes back to a positive 1, then it comes back to 0. And then the slope over here is minus, 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 minus. Therefore, this is C part. So what they're trying to say here is we can take the original function, and from knowing the slopes, the values of the slopes, we can plot a derivative equation. Okay. And we're going to look at example 31 and 32 where we can go backwards. If we're given the slopes, the graph of the derivatives, we can come back and come up with the original equation in a few cases. Not very often, but in a few cases in Calculus 1. Okay, now let's look at example 31. All right, problem 31 there in the notes. It says this graph right here that you're looking at is made of line segments joined end to end from a minus 4 to a plus 6. Graph the derivative function. Okay, now this follows what I just got through talking about. Graph the derivative function. All right, so remember now, when we're graphing that, we're graphing the values of the tangent line. All right. So, what is right here? What is the slope? Well, the slope is, see, we're going to come over here 4 and up 2. So the slope is 1/2. So the slope right here is 1/2. The slope here is 1/2. The slope's one here 1/2. The slope's here 1/2. The slope's here 1. So all the way from minus 4 over to here, the slope is a positive 1. Oh, so right there's the graph then. All right. If this is 1, then at 1/2. All right. So the slope is 1/2 here. Slope here is 1/2, slope here is 1/2, slope here is 1/2, slope here is 1. So there's the graph of the tangent line to the curve from here to here. Well, let's see. Wait a minute here. We got to have a little gap there. Now over here, what is the slope? Let's see. The slope over here is 1, 2, 3, 4. Okay, over a minus 1. The slope is a minus. Now, if you need to do the mathematics, it would be y minus the y. That's a positive 4. 0 minus 1 is a minus 1. So the slope is a minus 4. So 1, 2, 3, 4. So from here to here, the slope is a minus 4. Now I need to put a circle there. And I need to put a circle there. I'll talk about these corners in just a minute. All right, now, what is the slope from here to here? The slope is 0, 0, 0. So therefore, our line from here to here, circle, circle. And now, what is the slope from here to here? Okay, well, the slope is over 2 and up 4. So the slope is 2. So we come up here 2 and we go circle, circle. So the graph of the derivative of this curve is whatever the slope is, value of the slope, value of the slope, value of the slope, value of the slope. There it is. Value of the slope, value of the slope, value, there it is. Value of the slope, there it is. The value of the slope, value, there it is. Now, let's consider the dot. At the point right here, exactly 0, we do not have a slope value because there are many. There's a slope of a tangent line, tangent line, tangent line. All those only intersect this line at one dot. Therefore, this is considered tangent by definition. Concept of tangent line to another curve is it has one point in common. So, there it is. So we have many. Well, if we have more than one, then we don't have one, it says. Okay? It must be unique. Therefore, at these sharp corners, we have no derivative. All right, so we're plotting the values of the slopes, the values of the slopes, the values of the slope, value of the slope, value of the slope. All right, now let's look at 32. And what 32 is saying, hey, I'm going to give you the values of the slope. Now graph the curve. Okay. I'm going to give you the values of the slopes, graph the curve. All right, the problem says that we're going to graph starting at a -2 plus 3. Right? So that has to be given. Somehow they're going to have to say, oh, okay, you got to start somewhere. All right, so we're going to start at -2 plus 3. All right, so what is the slope from here to over here? The slope is a -2. Okay, so over here we're going to do a -2. Minus slope is like that. Slope is 2 to 1. So that means when we come over here 1 for x, okay, we're going to go down 2, which will get us there. All right. So there is a slope of 2 to 1, negative. Well, wait a minute. That's all the way to here. That's all the way to here. Even in here, the slope is... So this continues. Okay. Over here 1, I go down 2. Over here 1, I go down 2. So I'm going to get all the way to here. All right. This slope continues all the way from here over to here. Well, how much is this? This is 2, and this is 4. Hey, that's still slope. Oops, I'm sorry. The y value is 4. X value is 2. Slope is still 2. Negative. All right. Now from here to here, what are we doing? Slope is 0. That means line must just come straight across here. Here's the graph of the line. What is the slope of this line? 0. What's the slope of this? -2. Slope of this? -2. Slope of this? -2. All right. Now it says from here to here, the slope is 1. Slope is 1 means I come over 1, up 1. Over 1, up 1. All right. I didn't put in the slope here. In the original problem was a -1. So it says here, from here now, we're going to go slope of -1. So that's over 1, down 1. So we're going to end up there. So this is the original equation. Now let's see if that checks. What is the slope of this? -2, -2, -2. Well, there it is. -2, -2, -2. Slope here is 0, sure enough. Slope here is a +1, sure enough, 1, 1. Slope here is a -1, 1, 1. Okay, -1, 1. So this is how you can sketch a curve, the original function, when you're given these slopes. Sometimes, not always, okay? What happens is this. If this slope becomes a slanted line, then this becomes a parabola, a curve like this. Okay? It goes up 1. If this is y is equal to x, that's the slope, okay? Then the curve becomes x squared, a parabola. If the slope is a parabola, then the original curve becomes a cubic. Okay, this concludes tape 402.